Well, welcome to this video. In this video, we will try to complete the discussion on these Bell inequalities. So we talked about this lambda that EPR says must exist, which is some past factors that must have been taken into care when the particles were together, and they must have exchanged information based on this lambda such that the joint probability distribution can be factored onto Alice's part and Bob's part. And so what we can say about lambda is that it can be modeled by a probability density function rho of lambda. So this particularly goes to Bohm, where he has made significant progress and have shown the existence of this hidden variable theory. And it is a paper that has been cited in Bell's own paper. So we take the fact that lambda is a random variable having some probability density function. So rho is greater than equal to 0, and such that integrating over all the lambdas gives us 1. It can also be a discrete distribution, it doesn't matter. But as long as if we have complete knowledge of lambda, we can easily factor this probability distribution, and there is nothing called superposition. So now we use one more fact about the variables A and B that we have discussed in the previous video or last to last video, where A is the value of spin along Alice and B is the value along Bob. So the point is, as we are discussing singlet particles, we introduce the notion of this classical correlation. So you see, initially I have mentioned that this particle that decayed to give these two particles, suppose it has angular momentum 0, spin angular momentum as well as orbital angular momentum. So what must have happened is that this electrons, if we look about any axis, the angular momentum must be conserved. That is what classical mechanics we know. So this electrons, if its spin is along certain direction about a fixed axis, then the other electron will be having a minus of that value. So what this means is that the value of spin component about a particular axis A will follow this particular equation, that it will be negative for Alice versus Bob, because the axis we are taking is same. You see, the axis is not different, axis is same, and this is on the Alice part, this is on the Bob's part. So this kind of a relation must also be satisfied by the hidden variable theory lambda, because it is after all a classical relation. What this means is that suppose Alice performs measurement about three axes, axis A, axis B, axis C, and she gets a value +1 about A, -1 about B, and -1 about C. Conservation of angular momentum says that Bob should get value -1 about A, +1 about B, and +1 about C, so that sum of the values is always 0, because initially it was 0 to begin with. So this is a classical correlation, and we will try to use this notion. Now you can see that EPR is very much correct, in the sense that if we think about that Alice gets a +1 in her spin, she knows about this axis, Bob must get a -1, and they say that it is simply because of conservation of this angular momentum. So we are seeing that classical correlations already feels like describing these quantum superpositions and this spooky actions at a distance. So but we will try to calculate further using the calculation as done by Bell. So what we will do is that we will calculate the average of this particular product of these two random variables, and the average will be over all values of lambda, and it is simply given by plugging in the density function and the product here. Now in the next line we will change B as b comma lambda equal to minus of A b comma lambda using the fact that angular momentum needs to be conserved. So then we get this, and we get a value of this particular expectation. And what we do is that now we take the difference of this value for different axes. So we have three axes A, B and C, and we are taking the difference, the expectation value in this particular fashion. So this is given by just using this particular formula here. This minus sign that we had due to this angular momentum conservation will come out, and we will have product of A, but the axes will be different. One will have A, B, another A and C. So that gives us this particular line. And now we make use of a very obvious fact. First we take out this common factor out of this bracket and make use of the fact that the square of this random variable, which is random because of this unknown nature of lambda, but is bound to take value plus minus 1, the square of this variable is always 1, because minus 1 square is 1. So we can plug this square value inside, because it is just like plugging in an identity, and then we can take one of the a's inside, and as the axis is same, this a will make the this first term as 1 and will multiply with the second term. So that gives us this particular big integral. And now we make one more observation, actually many observations. The first observation is that this bracket can only be 0 or 2, because this is a random variable plus minus 1. This takes value plus minus 1. Their product can only take value plus or minus 1. So this is always 0 or 2. That means this is a positive quantity. And here we have product of these two, where this again takes plus 1, minus 1, and this also takes plus minus 1, and their product can take value plus 1 or minus 1. And this lambda, that is a probability density, it is always greater than equal to 0. Using these observations, we can forget this particular number 2 expression and write a new integration that I will call I2, and this integral I will name as minus I1, so as to cancel this minus sign here. So what we know about I2, some obvious facts are, because this entire thing is 0 or 2, it is a positive quantity, so it's like an expectation value of a positive quantity, so it is always greater than equal to 0. And second point is that it is always greater than equal to I1. This is because we have ignored this particular value, and this value would have only added a minus and would have reduced the value of this expectation at most. So it is greater than equal to. Equal to is also there. And the third point that we make clear is that this I2 integral, what we can do is we can take the entire integral inside the square bracket and use the completeness to write the first term as 1, and the second term can be, in the second term we will have a minus sign, and that minus sign can be flipped using the angular momentum conservation as this, and finally we get this particular result. So using the fact that I2 is always greater than equal to I1, we can say that mod of I1, which is mod of this difference, is always less than I2, and that gives us this final inequality. So this inequality is Bell's inequality, and the important point is that regardless of what kind of a hidden variable theory you have, this inequality is a bare necessity for that hidden variable theory to even make sense. Yeah, so this inequality is important for making sense based on the classical notions and statistics. But the point is, quantum mechanics doesn't follow this. You see, to derive this inequality, notions of lambda, which is a part of hidden variable theory, has gone inside. And so this is an inequality in hidden variable theory formalism, Now we can simply try to check whether this inequality holds in the quantum mechanic formalism or not. So that's what we will see now. So this is the Bell's inequality, and there are different forms of this inequality and there are different explanations. This explanation using this integration is what Bell followed. So now we know that as per quantum mechanics, the average value of this product of these values of spin component of Alice and Bob is of this particular form. This was derived in video on Bell 2. So we can simply use this in this particular inequality and see if the inequality remains true or not. So just plug in the value, we get a new form of inequality, and this inequality is now in the vector form, where these A, B, C are the axes of this Stern-Gerlach measurement, and this axis can be chosen to be anything. In particular, we can choose a particular, so it must be true for any kind of ABC axis we choose as per the inequality, if it holds or not. So we take a particular axis where A and B are orthogonal and C lies in between them. So C is like a convex combination of A and B. And for concreteness, we can take C to be pi by 3 or 60 degree, and we can simply do the calculation. We see that it doesn't hold. In fact, for any combination that lies within the cone, that is the convex combination, this inequality as per quantum mechanics won't hold. So there are a lot of values, for infinitely many values, for which this inequality won't be satisfied. So now we have turned the philosophical notion of hidden variable theory into a realistic notion that can be now experimentally measured, and such experiments have been performed using electrons, using these photons. And what is true is that quantum mechanical result that this inequality is violated is actually true, and hence hidden variable theory or hidden variable formalism actually doesn't hold. So that means the underlying notion of reality and locality as per EPR doesn't hold. So that's all for this video. In this video we discussed this Bell inequality. So that's it. In the next video I may try to give a different thought experiment for this Bell inequality. There are many thought experiments. I will try to give the one with coins. So that's it.